That's good. Yeah, go ahead.
And here. Okay, good. Thank you for that, Paul. And thank you for organizing this series. It's been so much fun, and I'm so happy that we have the rest of the year to go with it. All right, so as Paul said, my name is Rebecca Caldwell. I'm going to talk to you today about a global delta data set that we created and the environmental variables that predict delta formation on marine coastlines. This is work I did during my time at Indiana University. And as you can see, there's a large number of authors that put a lot of effort into this effort. And there's even more people that helped out along the way. This has been a large multi-year effort to create this extensive data set. But particularly, I'd like to thank Doug Edmonds, my advisor, for all the effort he put in, and also Sarah Baumgartner, who did a lot of additional effort on this data set. All right, so there's a pressing need for a robust global delta data set and to better understand the conditions that dictate delta formation and size. So lots of people live on deltas. They're very important natural resources. They're agricultural hubs and hubs for large cities. And for all of eternity, of human eternity, humans have always relied on deltas. And to this day, we still rely on deltas. This is why we need to better understand their processes and what dictates their formation and also their size. For example, presently, delta vulnerability to sea level rise is not the same across the world, and it may be dependent on regional environmental variables and even on delta size. And so to better understand what this vulnerability is, we really need a much larger and more robust data set. For example, this figure you see here in a previously published work, it shows what you're looking at is there's two parts of the graph. There's this green area where deltas have enough sediment entering their system in order to keep up with projected sea level rise. And then on the red part of the graph, you have deltas that are potentially sediment starved and vulnerable. Interestingly, you can see there's a relationship with size. The smaller deltas tend to be the ones that are more able to keep up, and the larger deltas tend to be potentially more vulnerable. However, we know that our current data sets are too small. They don't capture the full variability of the globe's deltas, and they also, unfortunately, are likely biased towards the larger, more steady deltas. So we really think it's important to fill out this data set. Maybe there's more smaller deltas. Where do they plot within this vulnerability? And furthermore, we need to better understand how they're going to continue to change as practices such as damming or other sediment trapping practices continue. A lot of these deltas are receiving less sediment with time. If they receive less sediment, they may be pushed down within this plot, which might push some of them into this red zone. So this is just one example of a present need for a larger data set. Looking to the future, coastal restoration techniques often involve creation of new deltaic land. As we continue to combat potential coastal hazards, one of the best ways to do this that we know of is to create new deltaic land. However, there are still gaps in our knowledge as to better understanding what type of delta land will be created, how large of a deltaic body will be created. So we need to get a little better at being able to predict delta size as we move forward with these efforts. Also, looking to the past, in data-limited scenarios, for example, in hydrocarbon exploration, we often rely on the prediction of past deposits, sometimes based on inferred environmental variables. And so here I have this cartoon to give you an example of what I mean. In the modern, we might observe this area here. I wrote seismic coverage. It could be any sort of data coverage. So we might have an area where we have data. There could be cores or outcrops and something we used that we were able to estimate what the past environment looked like. In this interpretation, maybe we interpreted that we're in a fluvial system near the coast, but we really want to be able to decrease the uncertainty with which we predict what's outboard or in our area of interest. Maybe we want to know if there's a delta, or not, or maybe that delta is big or small. And some of the ways we do this is by inferring what those past environmental variables were. What was the climate like? What sorts of sediment and water fluxes were entering the system? And then we can use this to better predict what might exist in this area where we don't have data. But in order to do that, we need to increase our ability to do those predictions. So today I'll give you a quick outline. We're gonna start with some motivating gaps in our current knowledge. I'll then explain the global delta data set that we created, which holds 5,399 modern coastal rivers, 40% of which form a delta. I'll also discuss 13 different controlling environmental variables that we included in our analysis. Then we'll talk a little bit about the analysis itself, which the main hitting points are we used a machine learning approach to result in empirically derived equations predicting delta formation likelihood. So how likely is a river to even form a delta? Only 40% of rivers form them. What is the delta surface area? So how large is the delta? And also, what's the delta topset slope? Because this is a variable that we've seen to relate to delta area. And then finally, potentially most interestingly, we'll do some conclusions and discuss the implications, some of the implications. Interestingly, I'm going to start with the findings. What did we produce? We produced a huge data set and maps which are available for use in current publications. We also formed these predictive relationships showing that delta formation is promoted by water and sediment discharge, and it's suppressed by wave height and tidal range. Delta area can be predicted by a positive relationship with sediment discharge and drainage basin area, and a negative relationship with bathymetric slope of the receiving basin. Delta area also exhibits an interestingly very strong negative power law relationship with topset slope, and topset slope in turn seems to be best predicted by a positive relationship with grain size and wave height. Now don't worry, we'll go through those results in more detail, but I just wanted to give you some of those results up front to keep you interested. Also wanted to let you know that these findings are available in current publications. This one publication over here in Earth Surface Dynamics, which came out last year. This hosts the majority of the delta data set. This would include where the deltas are, some of the environmental variables, and also these maps here. So we have these maps where there's hotspots of river mouth locations, and also where our deltas are. For example, you see this little dashed box here highlights an area of hotspot of delta formation in Southeast Asia. Also, just a few weeks ago, like Paul mentioned, we had another paper come out where Doug Edmonds was the first author, and this was a paper in Nature Communications. Within it, we include the delta area data and then also some deltaic population data. And we'll talk a bit more about that later. These publications also include data sets ready for you to use. We've got statistics and distributions, and finally, we've got some predictive relationships. So I wanted to put this out here to advertise the papers. Please go to them, please use our data. This is why we spent years creating it, and I'm really excited to see what the community has in store, analyzing and playing with this data. Okay, so let's begin. Deltas grow at river mouths, as we all know, where there's a net source of sediment that outpaces removal and accommodation changes. So the majority of sediment sourced to a delta comes from upstream, from this upstream river. However, some might come from downstream as well, from waves and tidal action. The majority of the sediment sink or removal from this deltaic system occurs downstream. It might happen as sediment bypass, potentially due to channel mouth processes, and could also relate to sediment removal due to waves or tides. However, we still don't completely understand the balance of all of these variables in a quantitative predictive way. Furthermore, accommodation itself and changes in accommodation are part of this sediment balance dictating delta growth. For example, basin depth, as set by bathymetric slope, is a way of quantifying the size of the bucket that this delta is growing into, and also accommodation changes due to sea level change and subsidence. And then when deltas do form, the mass balance of sediment should dictate delta size. Take a look at these two deltas. You see their upstream rivers or parent channels are relatively the same size. However, the deltas themselves differ in size. And so this suggests that there are additional variables controlling delta size. It's not just the size, the visual size of the upstream river. There's other factors at play. And there are two approaches that have been taken thus far, to summarize approaches taken towards better understanding this balance. And one of them is a mass balance approach. And this would be similar to filling a bucket full of water with sand and just doing the math to figure out the volumetric balance of how much sand turns into delta topset versus not. And this is, in a very simplified way, approaches taken when trying to plan for coastal restoration efforts that might build new land. All right, so one of these previous mass balance predictions I've shown here, and you can see here that the prediction is that delta size should be set by these two variables I talked about. At the top, we have the sediment entering the system. That's this QS, the sediment discharge variable. And then underneath, that would be divided by the area of the box that needs to be filled, which will somehow be related to sea level, subsidence, and this ratio, this incoming mass balance is adjusted by a few variables. One, importantly, is the fraction of sediment retained in the topset slope, and also a few others, porosity, organic matter. But I bring up this fraction of sediment retained because this is one of the most infamously difficult variables for us to constrain. We have very little control on understanding how much of the sediment entering a delta actually remains within the delta topset and thus creates new deltaic land. Other issues with this predictor is that it also assumes sea level rise, which has not always been true and is not actually even true. There are places on Earth today that are experiencing relative sea level fall. And it also assumes shallow to flat basins, which is not always true. A lot of these delta systems are in fact prograding into quite steeply dipping systems. A different approach, also quantitative, that can be taken is a predictive empirical relationship. This previous example that I'm showing you here was computed by Savitsky and Sato on 51 deltas, and not surprisingly, and excitingly, we see our two variables that we predict to be very important showing up. We've got a positive relationship with sediment flux and a negative relationship with depth, which in this case is a way to quantify the geometry of that accommodation to be filled. However, we also have this additional variable showing up in here, water discharge. And I would hypothesize that this might be related to what sets that FR variable in the previous relationship, this fraction of sediment retained in the delta topset. The water discharge entering the river might have some influence on the delta's ability to retain discharge sediment. However, gaps still remain. For example, this data set was relatively small and somewhat biased towards the largest deltas based on the data that is available. We know there's a lot more deltas out there and smaller deltas, so we could expand on this. And furthermore, basin depth is a decent measure of the geometry of accommodation. However, it's partially dependent on delta size itself. And what I mean by that is when basins are sloping, when the delta is small and say it's up here, it's going to have the measured depth as measured right off the shoreline is going to be shallower than the measured depth once the delta has grown. And so it's not really a completely independent variable in this process. And we hypothesize that a measure of the bathymetric slope might be a better, more independent variable to use. Furthermore, topset slope should control delta area by partially controlling that variable I keep talking about, this fraction of sediment retained in the topset. The reason this is because for a delta to maintain a steeper topset slope, such as this one down here, a delta must portion or partition a larger fraction of its sediment to aggradation into its topset in order to maintain that steeper slope as it progrades. And for this reason, steeper topset sloped deltas will have a higher proportion of sediment going towards aggradation, which means less sediment to go towards progradation, which is the process that creates more lateral area. And so this is something that we've shown in previous research, where the steeper topset slopes relate to this bird's eye view of the delta where it's smaller, and the shallower slope for the same sediment entering the system would create a larger area. However, our ability to predict topset slope remains inadequate. We do have some qualitative predictive relationships, We know that some upstream controls on delta topset slope might relate to grain size, a relationship we've seen through numerical modeling and limited field data, and also sediment concentration might be a control. Furthermore, previous studies have hypothesized that wave energy and basin depth might control topset slope, but really we don't have many, if any, quantitative predictive relationships. All right, so to recap, what gaps exist in our ability to predict delta growth? We have a complex interplay of upstream and downstream variables. These lead to delta formation or existence. When does a river form a delta versus not? They also set the delta area or topset size. And furthermore, what sets topset slope? And is there this interrelationship? Well, we know there's an interrelationship between topset slope and area, but how does this play out on a global scale? So the objectives of the study that I'm presenting to you today was to, one, compile a global river and delta data set, including delta characteristics and controlling environmental variables, and then two, analyze that data set to determine the environmental variables most significantly controlling delta formation, area, and topset slope, and form empirical relationships that are predictive. Now let's start with the data set. So to create this global data set, something the size of which hasn't been done yet, we used Google Earth imagery. So this is why this took so long. It was years of scanning Google Earth by eye, scanning all of the coastlines and looking at all of these different rivers entering the coastal system. In our data set, we're only including rivers currently that are 50 meters wide or greater. There are smaller rivers, of course, out there. And this is largely related to data availability. And for example, Landsat imagery is only available to a certain resolution. We use a geomorphic delta definition. So what does this mean? This means if you look down here, we define a delta as the location where a river meets the coast and is associated with a protrusion of land from the lateral shoreline. So if I zoomed out in this picture, you'd see this lateral shoreline trend would continue like this, but here's this protrusion associated with the river. We also could define a delta by a distributary system. So here's an example of a delta that doesn't protrude from the lateral shoreline, but does have a distributary system. And then of course, deltas can do both, which is this example here. And then furthermore, we mark the location of the main river mouth right here as our main mark of where the river mouth and delta are. And just to throw in there, we don't include systems that are, for example, tidal systems that are not connected to an upstream catchment, because the purpose of this study was to look at how this catchment connects to the coastline. All right, so as I mentioned before, this resulted in 5,399 rivers. If only we could have had one more, we could have gotten a nice, pretty number of 5,400. 40% of these rivers create deltas, resulting in a data set of over 2,100 deltas. And here's just a quick picture. You can plot these locations up on Google Earth if you'd like and scroll around and see the full variation and range of delta morphologies that exist on Earth today. While creating this global delta data set, we've now been able to create maps of global delta distribution and also river mouth distribution. And so here's an example of a map that shows you the hotter colors mean a higher number or density, and if you were to measure in a number per shoreline length of river mouths throughout the world, you see there's definitely a visually obvious peaks in the tropics, for example. And then here in this map, we have just the rivers that form deltas. And we can use these maps to visually observe hotspots of delta formation. So for example, I've boxed out the parts of the map that relate to this globally averaged latitudinal distribution. So what you're looking at in this plot here, this black line is delta likelihood, or in other words, when averaged per latitudinal bin, how many rivers formed a delta? This dashed line is the average for the whole globe, that 40% or 0.4 delta likelihood. And so these areas where the black line is to the right of the dashed line are areas of hotspots of delta formation, meaning not that there's more deltas, but that a higher ratio of the rivers that exist build deltas. And so these hotspots exist in the tropics, which might not be too surprising, especially down here in this extra hot spot of Southeast Asia, where we have a lot of rivers forming deltas. I was particularly interested to see this hotspot in, I guess you can't call it a hotspot, in the polar regions, but this area in the northern polar regions where rivers are much more likely to create a delta than other areas in the Earth. All right, so how did we measure delta area? As I mentioned before, we mark the main river mouth, which is the widest distributary. We also mark the upstream delta node. This node is marked based on the upstream most bifurcation of the parent channel. When there is, in cases where there's no bifurcation and thus no bifurcation to mark the node with, we take the line between these shoreline points, which I'll describe in a second, and we mark the intersection where the main river intersects with that vector. And so that vector is created using these shoreline points. The lateral shoreline extents, one on each side, are created where the inflection point of the protrusion runs with the regional shoreline. And then in cases where there is no inflection point because there's no protrusion, that lateral location is set by the lateral most distributary channel. And so here's an example where there's no protrusion. So this is the edge of the lateral most distributary channel. We also mark a fifth spot here marked as OB, and that's for open basin. This is the basinward most extent towards the open basin, and it's measured at a right angle from this shoreline vector. And so that we have the the downstream extent of the delta. So between these 5 dots, we've got a pretty decent delta area metric for all 2,100 of these deltas. We then take the delta area as approximated as the convex hull of these 5 points. And we've compared this metric to other previously published data sets of delta area, of which there aren't that many, and they vary significantly. And they tend to be relatively small, but our metric actually compares quite well with, for example, the Savitsky and Sato metric for those 51 deltas that was published in 2007. All right, so we also measure topset slope. How we do that is we use SRTM data to take an average elevation around the delta node. So we take the elevation up here, and then we assume a linear slope from the delta node to all 4 of these shoreline delta points. Taking an average of that, we have this average delta topset slope. I just wanted to quickly show you the distribution of some of these values. Here on the left, we've got global delta area values. And as we predicted, there's a lot of small deltas out there that we're not sure have been fully characterized previously. So I plotted a few of our more commonly studied deltas on here just to give you a sense for how big some of these commonly studied deltas are. Like the Mississippi, for example, one of the largest deltas in the world. But even the Ebro, which is a relatively commonly studied delta, and we think of it as somewhat small compared to a lot of the major deltas, but even that is still quite large compared to a lot of the deltas that are out there. And then furthermore, we've got these delta topset slopes here. I find it interesting to point out because we tend to approximate these systems as shallow, flat to shallow. We like to think of deltas as so low sloped, which they are, compared to much of the world, that we often ignore the slope of deltas. But in reality, there's a lot of really steeply dipping deltas out there. And it's an important parameter for a number of reasons that we need to start considering in our understanding and analysis of these systems. All right, so the environmental variables in the data set. There's a number of environmental variables that have been shown or hypothesized to affect delta formation. And so we did our best to capture as many as we can. Some of the upstream variables that we captured could be categorized as catchment characteristics. So these are variables that describe the upstream catchment within the river basin upstream of the delta. And then we also have some variables that I've categorized as river mouth input. So variables that you would be measuring and characterizing the river with at the location where it's starting to come close to entering the delta. For downstream system variables, we've got waves, tides, bathymetric slope, and sea level change rate. And just a quick explanation of where these data came from. The upstream variables, all of the upstream variable data that is measured came from this 2011 Milliman and Farnsworth data set, which the availability of the variables varies. So not all deltas, for example, have sediment discharge measured, or all rivers, they don't all have sediment discharge measured, but this is pretty ubiquitously known as one of the most comprehensive and well-vetted data sets of upstream catchment characteristics out there. And so we went through the effort of connecting all of this data with all of the deltas and river mouths within our data set, which was a pretty large undertaking. From this, we've also measured sediment concentration, and we have an approximation of grain size, which is an empirical relationship from the Savitsky and Sato 2007 paper relating grain size to upstream river length. For the downstream variables, wave height came from NOAA Wave Watch data. We've quantified wave height as the mean annual significant wave height. Tidal range, we've quantified this by using the mean tidal range variables coming out of TOPEX. And bathymetric slope comes from eTopo data. The bathymetric slope is measured as an average of slopes emanating from the delta front. So we take the elevation, well, the elevation at the delta coastline is 0 compared to mean sea level. And then we take all of the elevations or bathymetries at a moving radius around from the delta in the area immediately near it within about 20 kilometers that it's prograding into. And we use that area, those data to calculate a median bathymetric slope. And then we also have some sea level change rate variables. All right, now that we've created the data set, let's analyze it and to try to answer these questions about formation, area, and topset slope. So just to remind you, one of our first questions that we wanted to answer is why do some rivers form deltas and others don't? So we've been able to take all of this data and use a binary logistic regression to come up with an equation that predicts the odds of delta formation, which is this variable on the left, where this variable here is the probability that a river forms a delta. So this relationship shows that the majority of variation in whether or not a river forms a delta is set by 4 variables. And these were the only 4 variables of all the 13 that we tested that produced any statistically significant influence on the ability of a river to form a delta. Luckily, the variables make a decent amount of sense, so they're not too surprising, which is great because that means we can explain them. So from the upstream, we have both water discharge and sediment discharge that promote delta growth. The variables that suppress delta growth come from the downstream, wave height and tidal range. So this is the first time on a large global delta data set we've been able to show that the majority of the control of waves and tides is to suppress delta formation. And then I'd also like to show here that this y-axis is the measured likelihood of delta formation, whereas the y-axis is measured and the x-axis is predicted. And you can see that there's a pretty tight correlation between for our predictor versus what actually exists. And we have a 74% success rate. So this is pretty good results that I'm happy to see and see used. So what does this tell us about these controls on delta formation? Well, first of all, there's this first order control. There's this first order control from water discharge and sediment discharge promoting delta growth. that would be shown over here in these plots. What you're looking at is at the top is delta likelihood. So what that means is as the variable on the x-axis increases going to the right, as delta likelihood increases, this is telling us that higher water discharges and higher sediment discharges are increasing the likelihood of delta formation. And over here, we've got waves and tides. As those increase going to the right, delta likelihood decreases. Interestingly, these full observed variations in water and sediment discharge account for the full range of delta likelihood. So our largest rivers on the Earth are basically almost 100% likely to create a river. There's not much that's going to stop them. However, at the same time, wave height and tidal range have strong influence when they're very high. If you have a very high wave height in the area, you are almost completely unlikely to create a delta. With that said, the full variation of waves and tides only accounts for a 50% range of delta likelihood, whereas these other upstream variables account for an 100% full range, suggesting that these downstream variables are a secondary control to those upstream variables. Furthermore, removing waves and tides from that predictor I showed you recently only causes a 3% decrease in success rate, which suggests that it's really these upstream variables that are controlling the likelihood of a river to create a delta. All right, our next question, once we've got a delta, how big is it? We find that delta area increases with upstream sediment discharge and drainage basin area, and decreases with downstream bathymetric slope. So here's this predictor that came out of some machine learning. So we applied machine learning algorithms to it to create the manipulation of the important controlling variables that that best predicted the measurements and decreased the variation in those measurements. And so this prediction that we've got here has an R-squared of 0.95, which is quite impressive. Again, I'm very impressed to see that our mass balance comes out of this. So we've got this mass balance variable here, where sediment discharge is on the top, and we've got a negative relationship with bathymetric slope, which was the metric we used to quantify the accommodation or geometry of the basin that the river is entering. However, we've also got this additional control that's really important. So what this empirical relationship is telling us is that you really need more factors included to get a good estimate of delta area. You can't just use this mass balance. Additional work is needed to exactly untangle why drainage basin area, which is AB here, why this is the most important factor. And there's a lot of potential correlations here. There's a strong correlation between a previously known correlation between upstream drainage basin area and water discharge. So maybe water discharge is in there and that's part of what's setting delta area. There's also a potential connection with river length and grain size. So larger upstream drainage basins tend to have longer upstream rivers with longer transport distances, which tends to cause a decreased grain size of the sediment flux entering the coast. So this term could be capturing a grain size variable within there. All right, and then the next question, does slope influence delta size as we've predicted, and what sets delta slope? So we find that delta area exhibits a very strong negative power law relationship with topset slope. You can see in this, this plot here, on the y-axis we have area and on the x-axis we have slope, and there is pretty impressively low variation in the data given how large this data set is. This plot has over 1,300 deltas on it. So there's a very strong relationship between a delta's area and topset slope, which again is exciting to see because this is exactly what we've hypothesized from previous work. As I mentioned before, shallower systems should have larger areas because they don't have to retain as much sediment within their topset and have more sediment that they can put towards progradation. And progradation is the process that creates that large delta area in terms of lateral topset size. However, what sets topset slope? We find through the machine learning work that topset slope is best predicted as a combination of wave height and grain size and has a positive relationship with both of them. This is the least tight of the relationship. So we have an R squared of 0.5, which in itself, again, is quite impressive for such a large data set. But there's probably more factors that go into dictating slope. But this is the first time this relationship has been shown on a large natural data set. As I mentioned, the relationship with grain size has been previously predicted by theoretical and numerical modeling results. We've predicted that finer grain deltas will create shallower topset slopes, which create larger deltas, whereas coarser deltas create steeper slopes, which create smaller areas. And the relationship with wave height has previously been suggested in other work, but as I mentioned, this is the first time either has been shown to have a strong relationship on a large natural data set. All right, so our conclusions. Well, first of all, we compiled a large global river delta data set and formed the predictive relationships answering the questions, does a river form a delta or not? We saw that upstream variables of water discharge and sediment discharge are the primary controls. The full variations observed in them across the planet relate to the full variation in likelihood of delta formation. On the other hand, downstream variables of wave height and tidal range are secondary factors, but still very influential in whether or not a delta forms at a river mouth, in the sense that there's a negative relationship and they suppress delta formation. What size delta will form? As I mentioned, we have positive relationships with sediment discharge and basin area. In other words, the larger the drainage basin and the more sediment entering the system, the larger a delta is going to be. However, there's potentially some additional factors at play within this drainage basin area variable. And then on the other hand, we've got steeper bathymetric slopes creating smaller deltas, and also steeper topset slopes on the delta itself creating smaller deltas. So this inverse relationship with both topset and bathymetric slope is a really interesting geometric parameter or set of geometric parameters that need to be considered when trying to predict delta size. And finally, topset slope. How steep will the delta's topset slope be? We saw that there's a positive relationship between both wave height and grain size. Both of these relationships have been predicted previously, and this is the first time we've shown it on a large natural delta data set. All right, so let's talk about some implications of this work. First of all, as I've mentioned a few times, we've created the largest river and delta data set that we've seen yet, and it's available for your use. So there are 2 different publications currently with different portions of the data. We've got this eSurf paper that has the river mouth and delta locations along with 8 environmental variables. Here's an example of what the data looks like. All the delta and all the river mouths and deltas have IDs. There's delta presence flags, a latitude, longitude, the information for which Milliman and Farnsworth ID that delta connects to, as well as a bunch of these environmental variables. And then furthermore, in this Nature Communications paper that was published a few weeks ago, that's where you'd go to find the delta area data. And then there's also other data that has been collected within that paper. And so my request to the scientific community is to please use this data. I want to see what we all come up with and further our understanding of these global systems. Another interesting implication of this work is that it's helped increase our conceptual understanding of the constructive versus destructive forces forming deltas. So we very traditionally tend to think of deltas as river, wave, or tide dominated, similar to this tripartite diagram over on the right. We think that the results of this work warrant a slight recasting of this concept, in the sense that our data suggests that the most wave-dominated delta is in fact no delta at all. And so rather than saying wave-dominated or tide-dominated deltas, we really should consider these as constructive versus destructive forces, and where the balance of those constructive and destructive forces cause a delta to fall on this tripartite diagram might be better understood if we recast this question. And I stress the word recast because this is not a brand new concept. Researchers did have these ideas as early as the 60s and 70s. And so I think we've gotten a bit away from it, and we really need to think of it again as the most wave-dominated area, for example, having no delta at all, rather than a wave-dominated delta. All right, we've also got implications for delta reservoir presence prediction. And so this relates to that looking into the past idea that I threw out there at the beginning of this talk. So when looking into the stratigraphic record, we oftentimes want to predict what deposits exist in areas where we don't have data. And as we understand, it's very difficult to get subsurface data for this whole world, and we'd really like to get better at understanding what might exist in different areas. So we can use these equations to put additional quantitative constraint on deltaic reservoir presence uncertainty in data limited scenarios. So is there a delta? As we already said, not all rivers form deltas. So here we go. So we can use this, we could maybe use this prediction and see how well it is at predicting the presence of deltaic reservoirs. And interestingly, even if only water discharge and sediment discharge are estimable, this prediction still has a success rate on modern rivers and deltas of 70%, which is really good. So we could potentially be using this to decrease uncertainty when we're working on these sorts of predictions. We could furthermore use it to try to estimate how big the delta is. As we know, if the sediment discharge, drainage basin area, and bathymetric slopes are estimable via other methods, we might be able to further constrain how large the delta deposit would be. Furthermore, if slope or grain size and wave climate are estimable, we can try to figure out these relationships for past systems. We can also think of it the other way around. So what about scenarios where we know there's a deltaic deposit? We have good stratigraphic control. We see how large it is. Maybe we can use this to estimate other environmental variables that formed it. Furthermore, could we potentially say something about the internal deltaic deposit characteristics? So in situations where we have decent control on these other where we know the size of the delta, we know it exists, we might be able to get better at constraining the environmental variables that were there. And some of these environmental variables could be valuable to say something about what was going on upstream of the delta, perhaps what happened downstream of the delta as sediment continued through the ultimate source to sink system into the deep water. These variables are also known to have control on the internal characteristics of the delta. So in cases where data is limited, we don't have high resolution data. We know where the delta deposit is. We might know how big it is. Maybe we can use these relationships to better constrain its internal characteristics as well. Another implication is building new deltaic land. And as we mentioned before, this is a common coastal restoration technique, or it's becoming more common, and we're trying to get better at it. And we might be able to use this relationship to better decrease the uncertainty with which we build new land. In this hypothetical example, if a system has a probability of delta formation at 45%, we can predict that if all other variables were held constant, if you increase the water discharge by 600 meters cubed per second, you increase your likelihood of forming a delta to 54%, which is an 8% increase in probability, which is huge because these efforts are not only vital for our environment, but they're also very economically straining. So if we could use these understandings to increase the likelihood of success, I think that would be a really good step forward for us. All right, and then the last implication I want to talk about is the implication for further studies. So this paper I've mentioned a few times now that Doug Edmonds is lead author on, and I'm also a co-author on, it came out a few weeks ago. We were able to use this delta data set to say something about the populations that live on them and their vulnerability for a number of things, their relationship to tropical cyclone activity, to flooding associated with that activity, their elevations within these delta area polygons, and also related to their economic stability. So for example, this study, we've shown that 339 million people live on deltas. 89% of those people live in the latitudinal zone most exposed to tropical cyclone flooding. 92% of those people live also in countries with developing or least developed economies, often lacking hazard mitigation infrastructure. And then in an even further long-term thinking way, 80% of those people live on sediment-starved deltas. And so that's relating to that initial plot I showed you a long time, way at the beginning of this talk, where we were talking about whether or not deltas have the sediment flux necessary to keep up with projected sea level rise. And so you can see this plot here where we've added new data to that concept and recast it. On the x-axis is the area, the habitable area on a delta. The y-axis is sediment volume versus sediment needed. And so we can see that these larger deltas are not faring quite as well, which also happen to be the deltas with larger populations on them. Yeah, so 80% live on these sediment-starved deltas, which will be unable to naturally mitigate flooding through aggradation and sediment deposition. So these are an example of some of the work that we can do moving forward and utilizing this data set that we've created. All right, and with that, I'm going to say thank you. Thanks for bearing with me throughout this talk. We talked about a lot of things, and I'm really excited to hear what sorts of questions you all have.
Thank you, Rebecca. It's wonderful, and it's a great talk. And I think the audience maybe have many questions. I have a long list of questions, at least 10, but let's give it to our audience first. Let's see, if you have a question, I saw some question already type in the chat. Rebecca, are you able to click the chat and to see some questions?
Let me go back to, can I stop? Do I have to stop sharing?
No, you do not have to.
Oh, I see it. Yep, I see it. Okay, yes, I see the chat. All right, shall I just start at the top?
Yeah, Adelic asked you the question. Adelic, you want to speak out, or Rebecca, you can read the question? Rebecca,
okay. I was waiting to see if Adelic wanted to expand. But okay, so yeah, so how applicable are the equations in analyzing a particular delta since they are based on an averaging of data from many deltas? This is a very valid question, of course. All of these predictions have very good, pretty tight correlation, pretty low variance for the size of the data set. With that said, the variance, of course, means that not every delta will be perfectly predicted. So I urge people to use these equations in a way to decrease the uncertainty. So I don't think you're going to be able to perfectly predict an individual delta using these equations, but you'll be able to predict the uncertainty related, which in practical senses is very important for things like hazard mitigation or any large economic project for coastal restoration efforts, for example. The more we can decrease the uncertainty, the more comfortable everyone feels and the more confident we are in our predictions. So yeah, so I think maybe a balance of understanding how to use these equations is very necessary.
Okay, so before we jump to the next question for Tom Bianchi, so I would like to add a comments. As we all know in this field, back to the 1885, when Gilbert, the first scientific systematically studied the delta in a freshwater lake. This is back to 135 years ago. Then in earlier 1910s or 1940s, 1970s, the work studied the Mississippi Delta. And so particularly this tertiary figure we all know very well, but we do not have such kind of data set available like Rebecca and Edmond, what they did collected. Now, I think there's a lot of questions still. Many parameters from geology, from oceanography, haven't been really considered. But I think this is a very good start. We have already get a pretty good understanding. Even the confidential correlation rate only 70%, but there's a lot of space we can improve. And so I have some question later, but Tom, go ahead.
Well, very, very nice talk, Rebecca. I really enjoyed it.
Thank you.
I think your talents of being able to present things in the clarity at which you do are being missed in an academic setting. So that's fine that you're at an oil company, but you really have very a good ability to convey a message. Anyway, so my question is, again, I'd like to bring in some of the carbon questions to this. One is I'm just wondering how important wetland vegetation fits into this equation with sea level rise and the loss of wetlands or destabilization of wetlands, because even with these other fundamental physical forces, I'm assuming that the ability of vegetation to trap sediment is going to be a really important factor for the existence and persistent growth. I don't know how that gets factored in. I understand how these physical factors were determined to be the most important across this data set, but how does that factor in? Is that being underestimated?
Sure. So, okay, I have a couple things to say in regards to that. So in the initial mass balance prediction that was published by Paola et al. That I talked about, that prediction had organic matter production in it. So that's just an example of, yes, we as a community know it matters. We know it has an effect. Within our data set, as you already mentioned, of course, it's not one of the physical predictors measured. I have a dream of one day continuing to grow this data set. And I think the most obvious step or first step would be some sort of vegetation index using remote sensing data, some green index, or you know, a more, there are plenty of indexes to use out there, right? I think that would fit very well into this study. And then from a physical standpoint, I very much agree with you. I think marshlands will be very important in their ability to capture sediment, especially as sea rise continues to grow or to increase. In all reality, the answer is somewhere within our data, maybe. I mean, they might relate. I mean, it starts to get a little circular, right? Maybe they're within the delta area data. Vegetated deltas might also have different slopes than non-vegetated deltas. And then the one last comment is, this is a static study, right? So we are using static data. This is a snapshot in Earth's time. Things have lag, so we know that natural dynamic systems don't necessarily respond immediately to all of their variables. So that's also another factor that's going to influence the variability in these results. And I think the marshlands might be part of that story, not just the marshlands, but all of the vegetation, all form, like, you know, all variations of how vegetation affects it.
No, I think that's a fair answer. I definitely would like to maybe chat with you more about other things. It's fascinating, and thanks for a great data set for all of us to work on.
Great, thank you.
Michael.
Oh, okay. Yeah, no, it was a great talk. You know, one thing in your predictions of like the area and slope that I didn't see was Q water. The water discharge, because I would think the water discharge would flatten the slope and increase the of the area, and that's probably part of what's in your AB factor, is that sediment, is that water discharge.
Mm-hmm.
Also, when you grow things, you know, the foreset slope probably, you know, in front of your topset probably varies a lot with grain size. You know, I've certainly seen, you know, almost an order of magnitude change in that, and that's also going to affect the area. So, you know, part of how the grain size is feeding in is through changing that topset slope. Sorry, foreset slope.
Yeah, I 100% agree. I sort of, for purposes of time, and there's so much we could talk about, I did sort of talk lightly about the different subaqueous slopes. I did focus more on the topset slope because it's more measurable from available data. But yes, exactly. We know foreset slopes are related to a number of variables, grain size being one of them. They're also very set by basinal parameters. So, oh my gosh, sorry, I'm blanking now. Waves and tides and alongshore currents can very much influence the foreslope of a delta. So yeah, I think as we move forward, you know, my hope is to take that mass balance approach and this empirical relationship approach and connect them. And I started trying to do that by explaining the physics of the variables in our machine learning responses. But I think that is one of the areas that we would need to consider, is how the foreset slope is affecting the ultimate upstream processes and the area itself. And the sediment fractioning, the sediment fractioning between the topset and the foreset and the
right, because there's some modeling by like Carl Friedrichs and stuff on, you know, trying to fit those foreset slopes, and that may, you know, and I don't remember his variables, but they probably fit back to some of yours.
Sure.
You know, things like wave heights. Yeah.
Yeah, that's great. So actually, Rebecca, there's could be some more offshore parameter can also hook up your onshore or shoreline data that can provide us a big picture, the full understanding of the whole sediment coming down deposit and further extend to the on the shelf. For example, in some delta, there's a big longshore current will bring more sediment away from the river mouth and either go to the deep sea through the canyon cross shelf, but majority maybe a longshore drifting away from other distal center. So, but so far your data is a good, I will say a good first step, good startup. But many things you also can consider. For example, you show the 75% correlation, but if you apply the large river, if you separate the data from the large river system to the small river, particularly those episodic event driving river, you know, if you pick them out and then some large river like Amazon, Mississippi, Yangtze, you will get a much better correlation rate, much better than the 75%.
That's a really good point.
And some other thing is, in reality, we know a majority of the world large river were formed in the last 6,000 years when the mid-Holocene sea level high stand. But back that time, many large river delta is beginning from the apex. The apex is much further inland in a valley. And the data we found in the past 4,000 years or even 5,000 years, most of the delta propagate much faster, you know, inside a shadow, energy protection, you know, a shadow area. But nowadays, most of those large river delta now in an open ocean.
Right.
And like, for example, like the Irrawaddy, so Steve just talked about Wednesday and the recent project, even the Ganges-Brahmaputra. So now, even the same amount of sediment or water coming down, but the delta now is facing to a big ocean, you know, is a big ocean wave and tide. Right. There's a less and less sediment able to trap on the delta, on the topset, subaerial particularly. So the delta area increasing is sharply decreased.
Right,
so
for sure.
All those can be considered for future studies.
Yeah, so actually you bring up a great point, and in fact, from a purely theoretical standpoint, even if you remove the intricacies with which you talked about, even if you remove the concept of going from protected to less protected, if nothing changed aside from the delta growing, the growth rate will decrease through time from a purely physics standpoint. There is only so big a delta could, eventually the delta would have one grain going here, one grain going here, and it would, if there is a theoretical upper limit of an equilibrium delta area.
That's the.
Go ahead.
No, I think Paul, can I say something here?
Sure.
I'm sorry to interrupt, but I just thought that what you just said was sort of what I was trying to say before, except I didn't say it in the context of time. But that's exactly right, that with the wetland idea, that becomes more important with time, because in the more protected earlier stages, you didn't need as much wetland. But now, as you say, when you go to the more open coast, that factor becomes more important with time. Otherwise, the loss rate is so high. So that's kind of an evolving level of importance. Thanks for bringing that up, Paul. But I didn't say that before. And maybe my brain was I was thinking more in modern, but that's exactly another point to bring up.
Yeah, that's a great point.
Definitely the variable of this seminar series. We will nourishing, stimulate, many that kind of idea. Rebecca, Tom, we definitely talk about, even Michael, there's maybe next proposal or even a short summary paper about the equilibrium of the Holocene Delta. Let's see this. Nobody talk about this. We have to write a paper, look at what large river, the equilibrium status. And we have and also, as Tom and Michael know, we served so many Asian major deltas. We have a lot of offshore data. We can hook up of your onshore data set, as I mentioned, have a better, big whole understanding of the whole things.
Sure. Yeah.
To be honest, nobody like our group studied all the way from the Yangtze, from the Yellow, the Taiwanese rivers, the Pearl River, the Red River, the Mekong River, the Ganges, Brahmaputra, the Irrawaddy, nobody, So we have a lot of that kind of offshore data, so we can put them together.
Yeah, I would love to see all of this combined.
Yeah, that's good.
Any bias towards the larger rivers.
Sorry, say that again.
The offshore data is biased towards the larger rivers.
Yep, exactly.
Yeah, very good.
I guess we all just need to go back out in the field more.
Yeah.
Get more data. I think there was another question or two rather than how about analyzing paleo delta, which is visible today on land, was one other question that was in here. Yes, I get this was probably asked earlier, but yes, I think it would be great if we could analyze the paleo deltas. I'm not sure exactly what the question is referring to, if it's referring to deltas visible through outcrop on land, or if it means like signatures from that are visible aerially.
Okay, can I explain?
Yeah, great.
Hello. Yeah, actually, for example, it's visible from LiDAR data.
Mm-hmm.
Yeah, because I have a delta area which I'm looking at, and it is visible from the LiDAR, because I can actually even do a cross section from a topographic cross section. I can see the faucet and the slope, everything is visible, right? And from the LiDAR, yeah. So I was wondering whether those equations can be used in such a way that we predict, into the past instead of the future. Yeah, considering some of the parameters that created the delta. Is it possible to do that?
I think it's probable. I will not say with 100% sureness that it's possible, because I haven't done it yet. So we have not tested these equations on ancient deltas. I was trying to explain that they probably can be helpful. A full study would need to be done, but I think my personal opinion is that it would make sense to think about applying it this way. We've also have a past study where we were looking at older deltas. Ancient maybe makes them sound older than they are, but thousands of years ago, similar to what you're describing. And actually it's the delta that you see in my background. This delta is the modern version, but we've mapped out 4 previous versions of it moving upstream through time. And this is an area of the world where sea level's falling in Canada. So we have relative sea level fall in the north, right? And so we've done something similar where we've shown that the size of the delta has not changed much through time as it avulses around. So you see the old signature of the delta, and the sizes and slopes and whatnot are pretty similar to the modern and to its changing through time.
Yeah.
That's fantastic.
Okay, thanks for the answer. Thank you.
Yeah.
So Rebecca, if possible, please share this PowerPoint to this community. I think the student or your colleague will benefit a lot by your previous, published work. If you know any other question, so once again, I will say next Wednesday, we have a talk from Chinese colleague about the Yellow River Basin, and also Ruka from University of Leeds, UK, will talk about more the delta sequence stratigraphy. And so I think we can, if you know any other question, we can stop here. Thank you, Rebecca. It's wonderful. And thank you all the audience and our very loyal, customer, Tom, Michael. And so thank you for your support, and thank you everybody. So I see you next week. So
yeah, thanks for coming, everyone. This was fun.